Number 1. The force between two bodies have identical electric charges. The force between two bodies having identical electric charges. All right, so they could either be plus plus or minus minus. So what are they going to experience? They're like, yeah, repulsion. Yeah, it's like that uncle that you never want to see at Thanksgiving meal. Repulsive. So the force is repulsion. Right, we start off slow and pick up steam later. Number 2, atoms having equal or nearly equal electronegativities are expected to form, looks like a certain type of bond. So if we've got exactly the same element bonded to another element, or they're very close together, first of all, they should form, they're not going to form ionic bonds. It's going to be a covalent bond. But it's going to be a certain type of covalent bond. Polar. And that would be C. That worked, except I can't read the rest of it. So let me see here. Okay. Number 3. For the elements, cesium, fluorine, chlorine. Cesium, fluorine, and chlorine, right? Okay. Order of increasing electronegativity. So what's the periodic trend? You have your table here. You go over here like that, over here, you come there. What's the trend in the periodic table for electronegativities?
Increases left and right.
Right, goes like that.
Decreases top to bottom.
And decreases this way, so increases that way, right? Okay, so put together, they're like that, right? Lower left, upper right. Okay, so let's see where these guys are located. If we got to put them in order of increasing electronegativity. This has got to be the least one, right? Something's going to be bigger than that one because it's way down the lower left-hand corner. And then we know fluorine is the largest one at 4.0 on the poly scale. So it has to be it. B. All right. 4. The electron pair in CF bond could be considered CF bond. Okay. First of all, they're both nonmetals. So we expect a covalent bond, right? From that. Since we're not given the electronegativities, then we have to sort of make some assumptions. The electron pair in this bond is going to be, could be considered A, closer to carbon because carbon has a larger node. It would be closer to fluorine because it's more electronegative. B, closer to fluorine because fluorine has a higher electronegativity than carbon. Okay, we found our answer. And there are no squirrely ones in there like none of the above or 2 of the above. So once you find your answer, you can move on. Let's see, I'm going to scroll this one. 5. There we go. Which of the following molecules has no dipole moment? Okay. I guess we got to do all of them then. And then E is none. None have a dipole moment. Okay. Carbon dioxide. So what do you need to do to determine dipole moment? You need the polarity of the bonds and you need the geometry. So What do you have to do to get the geometry? Lewis dot structures. Okay. So carbon has 4 electrons, oxygen has 6 times 2 is 12, so 12 and 4 is 16. So we have a carbon, we have an oxygen, oxygen. That's 2, 4. That means we have 12 left over. So 2, 4, 6. If we put them all here around the oxygens, which you're supposed to do, work from the outside in, and then make your octets. So how do we make an octet here? Well, there are 2 ways we can do it. We can make a triple bond here and a single there. But we discovered, I think, in lecture that the formal charge on these 2 oxygens will be radically different from one another. And you want to be as close to 0 on everybody as possible. So I think we need to make a double bond here and a double bond here. And that'll leave us that, and this. And everybody's got an octet. Complete the circle. Now, how about the structure? Right? We don't have any lone pairs on the central atom, so whatever we determine to be the electronic structure is going to be the molecular structure. And if you have two pairs, 2 groups, that's linear, right? That's a linear structure. So even though oxygen is more electronegative than carbon, and it's going to have a dipole moment that way and that way, they're equal and opposite. Right? So this one is nonpolar. Is that what we're looking for? Which of the following has no dipole moment? Yeah, that one has no dipole moment. So E can't be it, because one of them does answer the question. Now, how about the others? Do you remember how to do ammonia? If we do ammonia, then we've got these hydrogens, right? So we have 5, 6, 7, 8. 8 minus 2, 4, 6 is 2. And hydrogens can't take any more hydrogen electrons. So we put them there. So that's 1, 2, 3. 4 groups is tetrahedral. And then we cover up the tetrahedron. Right? We got those up there like that, like that, like that, like that. Nitrogen in the middle, bonded to hydrogen here, the hydrogen back here, and hydrogen here. So if we cover that one up, we get a trigonal pyramid. And that means with nitrogen being more electronegative than hydrogens, the bonds are going to be polar this way. And taking them all together, plus that lone pair, then you get a dipole moment like that. Just in case we encounter ammonia again, then I don't have to explain it. But we'll do it now. So ammonia has a dipole moment. Can't be that one. Well, obviously. And then water, we've done water so many times before. It'll be like this, that. Okay, with a dipole moment like that. Okay. And then D, oh, is all. Right. So I guess we did have to do all of them, right? So neither one of those is true. This one is the answer. Okay. There's 6. I can do that one. 6. Which of the following has the smallest radius? Okay. A, B, C, D, and E. That was from a previous chapter, wasn't it? Atomic radius. Now we're looking at ions. So potassium plus, chlorine minus, rubidium plus, sulfur 2 minus, and argon. Now let's see, are any of these isoelectronic? Here's argon. Move one to the left, there's chlorine, so we got that one are isoelectronic. Potassium backs up to here, so that one is. Rubidium doesn't fit, right? So it's not isoelectronic with anybody. Sulfur, yeah. So all these guys are isoelectronic. There. What we have to do is say, all right, which of the following has the smallest radius? Well, remember the trend, atomic radius trend is they're bigger down and to the left. They get smaller, lower left, upper right. So rubidium, atomic radius would be the biggest because it's using. I'm not sure about rubidium because it's going to have how many 37 protons, and the rest of them are fewer protons. So when you strip that one electron off of the outer orbital, then rubidium shrinks back to the size of potassium, except that it's got more protons. So it's going to shrink. It's going to shrink smaller than potassium. Think. Now, based on that answer, it should be. Potassium should be the smallest one. And these are going to be big. That's neutral. That's got extra electrons. That's got extra electrons, and they're all isoelectronic. So we know amongst these four, that one's definitely the smallest. My question is rubidium, because potassium only has 19 protons. Oh, no, it's still got a bunch of electrons, right? This only brings it down to 36 electrons, right? And this brings this one down to 18. Okay. Right. So it's still got a bunch of electrons out here. Right. It's going to be too big. Potassium's the smallest. I was convincing myself. 7. Let's scroll 7 and pick up 8. All right. 7. Which of the following arrangements is in order of decreasing size? Oh, now they're getting nasty. Decreasing size. Okay, let's see what we got to choose from. Let's see, gallium 3+. It's in the rest of them. Calcium 2+. There's calcium 2+ in every one of them. Yes. Potassium 1+. Is it in every one?
No. Cl- is in every one.
Okay.
Then
Sulfur 2-. Okay, so we just need to find their order, and there are no oddballs in there that aren't in every one. Okay, so we're looking at decreasing size. All right, the decrease. Let's see if there are any isoelectronic in here. Calcium 2+. Gallium 3+. Yeah, those are isoelectronic because they're on the same period and they're backing up. So they're going back there up to here. The reason gallium is 3+ and it's isoelectronic with argon is no, it can't be, because it's got d electrons. These d electrons and argon doesn't have. So these are not isoelectronic. I'm sorry. The charge would indicate, but they're not. Okay, these two are isoelectronic. Chlorine is isoelectronic with that, and sulfur. So gallium's the outlier. Okay, let's see if we can figure out their sizes. All right, if they're isoelectronic with argon, then the difference is their nuclear charge. 19, 17, and 16. So if they've got the same electronic structure, but this one has a higher isoelectron that has a higher nuclear charge.
so you just have to look around other ways, decreasing size.
Yeah, but these are in. Yeah, I think that's sound reasoning. Which of the following arrangement is order of decreasing size? This should be the smallest, I think. This one is smaller than that. Because it's got 31 protons. And it has 3D, but it's it's lost its 4 P's and 4 S's. They're gone. So this is down into a smaller orbital size too. So this one should be the smallest. And then the next one would be all right, what's the atomic trend? Right. Small from lower left to upper right, correct? So if we look at it that way, lower left, upper right, potassium, calcium, gallium, sulfur, and chlorine. And if this one loses 1 electron, but these are gaining electrons, right? So they're going to balloon out. So these two, because they're charged, could be the larger ones. So I would put sulfur first, chlorine next, and then I'd go after these guys. This one with a 3+, this one with a 2+, this one with a 1+. So they're decreasing, yeah. So would that be the right order? Yeah, I think so. Put this group right here, down there. Now, the only way to be absolutely sure is to get a periodic table with the sizes on it, ionic sizes. We're just sort of spitballing here. In reactions between magnesium and sulfur, the magnesium atoms what become anion? Okay, magnesium, right, and sulfur, they're both solids, but this one's a non-metal and this one's metal. So the electrons are going to transfer like that. Magnesium and sulfur, magnesium atoms become cations. They lose electrons. All right, let's see. Good night. Choose the molecule with the strongest bond. Okay, looks like we got all halogens there. We've got this one, this one, this one, and iodine. Yeah. They're not all equal. First of all, you get increasing electronegativity as you go up. So increasing electronegativity should strengthen the bonds. But remember, at the same time, you're decreasing the size. So one of the things that affects the strength of a bond, particularly ionic bonds, but it also has an impact on covalent bonds, is the size of the atoms. Right? So we're shrinking the atoms as we go up, but as we go up, the electronegativity difference still wins out. And greatest bond energy. That's okay. Let me stop here for a second. When they say bond energy, that's a technical term that means how much energy does it take you have to put into the bond to break it. Right. So when we say bond energy, we're not saying the energy of the bond is up here. We're saying the energy of the bond is actually down here, and it takes a lot more energy to break the bond. In other words, bond energy, high bond energy means it's more stable. It's actually at a lower level if you put it on an energy diagram. I ran into that problem. I'm sorry?
We're actually looking for the strongest bond, not bond energy. That's the 10. We're not doing that one.
No, the bond energy is right. It means the strongest bond.
Okay.
The greatest bond, yeah,
Okay,
greatest
same
bond energy. You're right. So we're looking at these different bonds. And we find that the electronegativity increases as you go up. Right, we know that trend. So the electronegativity increases, so it's the strength of the bond is going to go up from here to here to here. We expect it to go up also to here. The problem is the fluorine atom is so small. Let me see. I'm searching for the right word, so I'm going to have to fudge. One of those days. Okay. Now it makes sense to me. I'm gonna try to make sense to you. As these atoms get closer, as they're trying to form a bond, they still have nucleus in each one of them, right? So we have fewer electrons out here to shield the positive charge from either atom. So you start to get repulsion. And in fact, when you get closer together, you don't just get proton repulsion, right? You also get electron repulsion in the bonds itself. Well, and the core electrons. So you start to get repulsive effects that outweigh the electronegativity. So this one has the strongest bond of all of them. It's counterintuitive. All right, let's see. 12. Let me just, while I'm here, scroll it up so we can get 12 and 13 both. 12. These molecules have a zero net dipole moment. Oh, I shouldn't have done that because we have to look at those guys right there. Draw the Lewis structures and use them to answer the following questions. Okay. And 4 and 5. Okay, so we got boron trihydride. We've got nitrogen dioxide, sulfur hexafluoride, ozone, and phosphorus pentachloride. All right, boron trihydride. So boron's got 3 plus 3 is 6 electrons. I'm gonna count the electrons first. This is 5 plus 12 is 17. Right. This is same as oxygen, 6. 6 times 7 is 42, so 42 and 6, 48 electrons. This one has 3 times 6 is 18 electrons. Phosphorus is the same as nitrogen, so it has 5. And 5 times 7 is 35, so it has 40 electrons. Okay, now we can draw our structures. Boron, like that, 2, 4, 6, that's it. We're done. Oh, we have to net dipole moment. Okay, so we'll come back to that. So this one has a nitrogen and an oxygen and an oxygen. So that's 2, 4 minus 4, which is 13 electrons. 2, 4, 6, 8, 10, 12, 13. What do we have there? We got a free radical, an unpaired electron. This is an extremely reactive molecule. That's just side, this doesn't answer the question. SF6. So we have 1, 2, 3, 4, 5, 6. Fluorines. Okay. All right, 2, 4, 6, 8, 10, 12. We have 6, 36. We have 2, 4, 6, 8, 6 times 6 is 36. So that takes care of it. Put 6 around each one. There we go. Ozone. We have O, O, and O, so that's 2, 4. It's 14, 14. 2, 4, 6, 8, 10, 12, 14. Let's see. I didn't make double bonds here or anything, so this one doesn't have an octet yet, and it's probably not going to have. But we could, as 2, 4, 5. So it needs 3 more electrons to make an octet. If we put these 2 over here, did I do that right? You know, 2. Yeah, doesn't have a charge on it. That would make this one a double bond. Right. That's gonna knock that, that's gonna knock that. This one has 2, 4, 6, 7. That one's deficient. Okay. Let's see. This one. We need. It's 2, 4, 6. So we just need a double bond on one side. And that should give us octet 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And then PCl5. Okay, 2, 4, 6, 8, 10. So we have 30 left over. 1, 2, 3, 4, 5, 6. 6 times 5 is 30. Okay, so if we make an octet around each one of these chlorines, we'll use up all of our electrons. Okay. So now the structures, right? This is trigonal planar. Right, so it's a regular shape, is no dipole moment. None. This one has 1, 2, 3, so it's trigonal planar, electronic. Okay. And if we cover that up, it's bent. So this one should have a dipole moment. Nitrogen and oxygen, they're really close to each other. Those are not polar bonds though, are they? Nitrogen and oxygen, they're so close. I think this one's nonpolar also. Yeah, well, I just look at the answer and they say it is. So they're saying that oxygen is sufficiently polar then oxygen is sufficiently polar, so it's gonna make a dipole moment. All right, so I question that one. This one is 6 around the central and no, so this is octahedral. And it's a regular shape, so even though the bonds are polar, this one's non-polar for sure. How about this one? 1, 2, 3. So this one's going to be like that. All right, I'll leave the extra electrons off. The problem with this one is that lone pair. All right, so the bonds are non-polar. So I would speculate that this one would be non-polar also. Except they say it is polar. I think what they're doing is they're saying it's polar because of that lone pair. So let's say this one's polar. And this one, it's a regular shape with 5. What shape do we get? Scratch the brain. A trigonal bipyramid. We have this triangle in the middle, and then we have something up here and something down here. Chlorines around the center, and then phosphorus in the middle. So they're all, even though they're polar bonds, they're all regular shapes, so they're non-polar overall. So if we go with them, they say 1, 3, and 5. Right, 1, 3, and 5 are 0 net dipole. Yeah, That's definite. The others are kind of iffy. I would say this one's non, but they say it is. So who am I to argue? Okay, 13. Let's see if this one's straightforward. How many electrons must be shown as bonding or non-bonding in the Lewis structure whose skeleton is? All right, we got 4 carbons. And then we have an oxygen on the end. And we have 3 hydrogens here, and then 3 around this one. Okay. So how many electrons? What they're saying is count up the valence electrons. That's all that means. It's just weird wording to see if you're paying attention. So we got 1, 2, 3, 4, 5, 6 hydrogens. 1, 2, 3, 4 carbons. 4 times 4, 16, right? And then a 6 for that one. So this would be what, 22, 28 electrons? Yep. Let's see, we're gonna need that. I got a funny feeling. We're gonna run across that one again. Oh, no, it's this one. Okay, that's all right. We'll move on to 16 then. But don't eat up in your lab time. In the Lewis structure for ICl2 minus, how many lone pairs of electrons are around the central iodine atom? So they tell you which one's in the middle. Iodine. And we have chlorine and chlorine. So we have what? 3 halogens, 3 times 7 is 21, plus 1, 22 electrons. So we used up 2 of them. Excuse me, 4. 4, that's 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. They're right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay. So how many lone pairs are around the central atom? 1, 2, 3. 3 lone pairs. Now, if I ask you for how many electrons, it's 6, but there are 3 lone pairs. All right. See if I can do. I did the old-fashioned way. There we go. 19. How many resonance structures can be drawn for the molecule ozone? Okay, we did ozone just a minute ago. Let's see. 18, 2, 4. 2, 4, 6, 2, 4, 6, 8, 10, 12, 14. So we can either do it like this, right? Or we can do it like this. So there are two resonance structures. Right? The double bond can form on this side or it can form on this side. So there are only 2 resonance structures that are available for ozone. 20. Okay. Which of the following types of molecules always has a dipole moment? Okay. Take them one at a time. Linear molecules with 2 identical bonds. No. No, those always has a dipole moment. Now, they could. If they're talking about the arrangement of the atoms themselves, then you can have. Can you have linear with lone pairs? Yeah, if you have two lone pairs. No, that was out. That can't be. Following types of molecules always has a dipole moment. Okay, so linear molecules with two identical bonds. No, they cannot be. How about tetrahedral? Four identical bonds equally spaced. Yep. They cancel each other out. How about C? Trigonal pyramid molecules, three identical bonds. Okay, how do you get a trigonal pyramid? You have to start from a tetrahedron and have one lone pair, like ammonia. That one should always be a polar, have a dipole moment because of that lone pair. Okay, none has a dipole moment. We found our answer. Let's see. All right, scroll to get 21. How about 22? And squeeze 21, 22 in there. All right, which set contains atoms listed in order of increasing electronegativity? So we got some oddballs. Yeah, fluorine, nitrogen, carbon, silicon. Increasing electronegativity? I don't think so. Because of that one. It should be on the other end. How about this one? P, N, O, and F. Okay, F's in the right place. How about P and O? P's lower left, then nitrogen, then oxygen, then fluorine. Yeah, this one's good. Yeah. Oh, we found our answer. (22) Which choice has bonds listed in the order of increasing bond energy? Okay. The ones that take the most energy to break. Right? The strongest bonds, the most stable bonds. Okay. If we have HF, HCl, and HBr. Now, when you are talking about fluorine with hydrogen, you can use electronegativity exclusively because this one's only got one proton and it's shared its other electron, so it can get close and still not be a problem. That's the wrong direction. It should be the other way around. If we're going from increasing bond energy. Okay, how about this one? Yeah, that's a good one, right? Single, double is stronger, triple is stronger still. That's a good one. They're not all the same, so I think we found our answer. It'd be B. I think in the work problems, I go into more detail. So if you want to answer the rest of them, see why they're eliminated, then you're welcome to check it out. Let's see, 23. In the gaseous phase, which of the following diatomic molecules would be the most polar? Most polar. Okay. So we got to compare all of them to see which one's the most polar. Oh. That's something of a no-brainer. You want the atoms that are the farthest away from. They're okay. In the gas phase. Okay. That's important. If this was in its most stable form at room temperature and pressure, then this would be a solid. But we're gonna we're gonna turn it into a gas. That means now the molecule is independent of all other molecules. It's just this one with that one. That makes a difference in how you approach this, because that would be an ionic compound if it were a solid. So now knowing that, and all of these look like they're ionic, except they're in the gas phase. The bond would be the most polar for the two atoms that are furthest apart from on the periodic table. Cesium's way down there in lower left, fluorine in upper right. So after that little explanation, then we're good. Let's see, 25. Which of the following ionic compounds has the largest lattice energy? The lattice energy most favorable to a stable lattice. So remember how we form the lattice energy? You have the gaseous cation and the gaseous anion, and they meet and they form the ionic solid. And the amount of energy they give up is always exothermic. The amount of energy they give up is an indicator of the strength of the bond. The more energy they give up, the more negative the delta H, the enthalpy, the stronger the bond. Is that what we're looking for? Largest lattice energy. Okay. So we want to look at, again, which ions are furthest apart. And not only that, but the size of the charge and the size of the ion. So we want high charge on each of them, and we want small size because of Coulomb's law, right? The force of attraction is proportional to the strength of the charge. So if you have single charges and double charges, the double charges will be stronger in attraction. And then how close can they get together? So the smaller double charged or triple charged ions will give you the strongest lattice energy. So let's look at what we've got. Barium oxide, beryllium oxide, cesium iodide, sodium bromide, and barium sulfide. Right? So cesium and iodine are both going to be single charged. These are single charged. This is a double charge. Minus. This one is 2 minus 2 plus. And this one is 2 plus and 2 minus. Okay. So I would focus in on these guys here with the double charge first, and then say which one has the smallest ions. Sodium and bromine are in the third period. Bromine is actually in the fourth period. So this one is real way too big. Right, we can count that one out. How about oxygen? Barium. Oh, barium is barium is massive. So count that one out. So beryllium and oxygen are the smallest ions of this group. That would be the highest lattice energy right here. This one. Is that right? B. That's what they say. That was an exercise in Coulomb's law. 26. The first electron affinity value for oxygen is blank, and the second electron affinity is blank. Unfavorable, favorable. Okay. So the first electron affinity, we need oxygen in the gaseous state, monatomic. Okay. And then we're going to add an electron to it, and it's going to make this ion in the gaseous state. And when the electron comes from infinity down to oxygen, it's going to give up a certain amount of energy. It's going to be exothermic. And the second electron affinity value would be like this. We didn't talk about that much when we talked about electron affinity. We just did the first one. But the second one is going to do this and make this one. Okay. All right. So is this one going to give up energy? The thing about it is, oxygen's already got one electron. Now, it does want the other electron. Make no mistake. Overall, the electron affinity for 2 electrons is favorable, but each step is different. This one is favorable because it's neutral, capturing an electron. But this one's already got a negative charge, trying to capture another electron. This is unfavorable. But for both of them, we add them together. And if we have the actual numbers, then we find out that overall they're favorable. But that's not part of the question. I'm just adding that. So it should be favorable, unfavorable. D. Okay. Primarily because of that second electron has to fight its way past the negative charge that's already there. 27. Let's do this. Okay, 27. I'm going to run out of time as usual. Let me see how many more I got to go, because I don't want to kick biology class out of here. I'll move as quick as I can. Using the following reaction data, calculate the energy of HF bond. All right. What's the energy of the HF bond? The HF bond would be the amount of energy it takes to break the bond. So HF would break into H and F, and these would be gaseous, and this would be a gas. Right? They need to be a gas because when you add energy to them, you want to assess the energy that's breaking the bond, not the energy that's changing their state. Okay. So if that's our target equation, let's see. HF we want on this side. Right, so we want to flip this one to HF gas yields H2 gas plus F2 gas. And now that will be a positive 542 kilojoules. Okay, but we only need one of these, right? So we need to take a half of that, which would take a half of this. Okay, I guess I better do that. This will be HF yields 1/2 H2 plus 1/2 F2. And this would be one, I need to go the other direction. This would be 271 kilojoules. Okay, so we're going to use this one, and we got that taken care of right there. Now we need to put these on that side. Right, so the next one puts 2 hydrogens on this side and an H2 on this side. Right, but we only need 1 hydrogen over here, so we got to take this one in half. But it's already oriented properly, so we just need 432 divided by 2, which would be 216 plus, yes. So we're going to use this one, and That takes care of the one hydrogen here and there. And half of this one takes care of half of that one. Okay? And we do the same thing for fluorine. 2F gas. And its value is 154, but again, we only need half of it. We only need half of that. And that half cancels this half and leaves us with one fluorine here and one fluorine there. But half of this is 77. So we just add those three together. And that'll give us the energy of that bond. If I did my math right. 271, 216, and 77. 564. 564 kilojoules. And that's usually per mole. Okay. Seems like a lot of work, just one little answer. That's the nature of the beast. People that do this for a living probably do that calculation in their heads. Okay, 28. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? Ooh, okay. CH3OH. I know that is stable. You know what that one is? Methanol, wood alcohol. So we could draw the Lewis structure, but how about we draw CH2O? It's that one. That's formaldehyde. It goes like this. One, like that, like that, like that. This one goes like this. And then O and then H. How about CH3O? I don't even know what that is. This is 4 and 3 and 6, so there'd be 13 electrons. So if we put carbon in the middle, oxygen here, 2, 3. Like that. Oh, excuse me. Mini oxygen. Amount of hydrogen for the change. Okay, 2, 4, 6, 8. Minus 8 is 5 electrons. So we need 2, 4, 5. 6, 8, 10, 12, 13. That's right. Okay. So why is it not stable? Well, these guys are happy. Right? They got their duets. Carbon's got an octet. Oxygen doesn't have an octet. It's not going to get one because it needs another electron. So if we do the formal charge for these, that'll give us some more information. Right? These guys are, they go in with 2, they go in with 1 and they get 1 back. So they're all zeros. This one goes in with 4 and it gets 1, 2, 3, 4 back. So it's a zero. Formal charge. This one, oxygen goes in with 6, right? It only gets 2, 4, and it gets 7 back. So this is a minus 1. That would make it unstable. Plus, it'd make it a free radical. Now, that doesn't mean it doesn't exist. It's just, it's not very stable. C2H2, that's acetylene. Oh, excuse me. Yes. That's acetylene. It's stable until you mix it with oxygen and light spark. C3H4. I'm not sure what this one is. C3H4. So that would be 3 times 4 is 12, and that would be 4. So we have 16 electrons. We have 3 carbons. And where are we gonna put the hydrogens? 4 hydrogens, like this. Yep. Okay, 2, 4, 6, 8, 10, 12. So we have 4 electrons left, and they have to go 2, 4, 6, 8, 2, 4, 6, 8. But this carbon only has 2 pairs, it needs 2 more pairs. So we just make this one over here, double bond, make this one over here, double bond. And I can't remember the name of that one, but that is a valid structure. Okay, so C. C would be the best answer. Simply because its formal charge is wacky. That's a chemical term. When your molecule goes wacky. Let's see, yeah, I can get all that up there. 29. Using the following electronegativity values, select from the following group the molecules that, I gotta move this thing out of the way, that fit the given statements. Given statements. Okay, so we got these 1, 2, 3, 4 molecules and none. The molecule, this molecule contains a carbon atom with a trigonal planar geometry. Oh, okay, I see. You don't need the electronegativities to do that. Right, so that's blue smoke. You can do it from the formula itself. Which one has a trigonal planar geometry? CH3CHO. Okay. CH3CHO. In this case, we've got 2 possible centers of geometry of central atoms. We have this carbon and that carbon. So this carbon, let's see how many we've got. 1, 2 is 8, and 4 is 12, and 6 is 18. 18 electrons. Okay, so we've got a carbon, we've got a carbon. The way we write organic compounds, those hydrogens belong to that carbon. And this hydrogen and that oxygen belong to this carbon. Right, that's convention. So we got these hydrogens here, right? That's tetrahedral. And we got this carbon with a hydrogen and an oxygen. Right? 2, 4, 6, 8, 10, 12. 6 electrons. All right, we have to put them over here. 2, 4, 6. And then to make this octet, we have to move that 2 over here to make that double bond. Okay. So 1, 2, 3, that's trigonal planar. Okay. Yeah. We know carbon dioxide is linear. CH3Cl would be tetrahedral. C2H6. C2H6. 1, 2, 3. 1, 2, 3 for your hydrogens. Okay. Those are both tetrahedral. So that's the only one. A is the only one that has a trigonal planar. I forgot to ask you guys if you had well, I did ask if you had trouble, but are any of these problems that we need to get to before I run out of time? Okay. Let's see. Ooh. Let's see here. Of the following, which molecule has the largest bond angle? Oops. 34. All right. Ozone. Like that, isn't it? This one is going to have it's going to be a bent molecule. So this one's trigonal planar, which means the angle is going to be what? 120 degrees, isn't it? 120, 120, 120 is 360. So this is 120 degrees. How about B? OF2. So this is 14 plus 6 is 20 electrons. So we have an oxygen in the middle, fluorine here, fluorine there, fluorine there. And I bet we have completes here. So that would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, so everybody's got an octet. That means that this one is tetrahedral. And if we cover up the electrons, then we get the same situation as with water. We get a bent molecule. Don't need to draw that, I guess it's better. And we have the oxygen in the middle. We have fluorine up here. Let's put a fluorine down here and a fluorine here. And then on the back side, we have a lone pair and then a lone pair up here, up top, to form the tetrahedron. So if we cover up those, we get a bent molecule here, here. And the bond angle is 109.5. That's probably less than that, but that's nominal. Okay, so this one's still the biggest one. C, HCN. Remember that one? That's a linear molecule. So that's 180 degrees. And D, water. Water is like this one. Starts off as a tetrahedron. So it has that one. So this one, more than one have equally large bond angles. Well, they have equals, but they don't have the largest. C has the largest, 180 degrees. All right, 30, nonpolar overall, 35. So we have SF4. Oops, like a charge. Here we go. So we have SF2. We have C, Cl4. We have H2S, and we have O, Cl2. Okay. Non-polar overall. Well, we know this one is tetrahedral, right? We've drawn that one before. And there are no lone pairs in there. So this one is non-polar. Definitely. This one's going to be bent like water. So it's polar. Do I need to draw them? It says, which of molecules? Oh, we found our non-polar. This one right here. Yep, it's tetrahedral. Let's see if I can squeeze another one in here. We're still waiting on lab partners though, aren't we?
Yeah.
So I'll just keep going. I don't think they need this room until 5 o'clock. Or is it 3 o'clock? Maybe it's 3 o'clock. Which of the following molecules are non-linear? Non-linear. NO2 minus C2H2 N3 minus HCN CO2 and H2O2. Okay. Let's pick out the ones that are linear. This one's acetylene. That's linear. This is hydrogen cyanide. That's linear. Carbon dioxide. That's linear. Okay. We know that for a fact. How about these others? NO2. 5 plus 12 is 17 to 18 electrons. So we have NO, O, 2, 4, 14. That's 12. So we need 2 more. there. That was nonlinear. Because we got three groups around here, and the molecule is going to be bent. It's trigonal planar, electronic, and bent. Molecular. Okay. How about N3? So we got 15 plus 1 is 16. N, 2, 4, 12, 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 14, 16. Okay. For this one, is that right? Oh, plus 1. We need 17 because of that negative right there. So we need 1 here. All right. That makes this one trigonal planar and it's bent. That's a free radical. And then H2O2. I see 2 plus 12 is 14. Right. Oxygen, oxygen, hydrogen, hydrogen. 2, 4, 6, 8. 2, 4, 6, 8. So this one, that part, that looks like a water molecule. It's going to be 2, 4. This is tetrahedral, but cover up the 2 and you get a bend. So this one's bent and this side's bent. Right. So that was nonlinear. So which ones are nonlinear? NO2 minus only gives us 2.
She said she was on her way like 15 minutes ago. She should be here in a minute.
Okay. I know this one's nonlinear. And this one's nonlinear. Why doesn't it put this one in there as nonlinear? Did I do it right? Let's see. Nitrogen is 5. 3 times 5 is 15. Oh, 16. Yeah. So we move this over here and this over here. And we get 2, 4, 6, 8, 2, 4, 6, 8. Okay, I drew it wrong. That was linear also. My mistake. So the only 2 nonlinears are on either end. Let's see. 38. The molecular structure of BRF6 plus. BRF6 plus is what? Okay. So these are all halogens. That means 7 times 7 is 49, minus 1 is 48 electrons. So we put bromine in the middle. And we have 1, 2, 3, 4, 5, 6 fluorines. Uh, 2, 4, 6, 8, 10, 12. That's right. That's 36. If we put 6 around each fluorine times 6 is 36. That's gone. So this structure, 6 groups is octahedral. C, octahedral. (39). What type of structure does XeOF2 molecule have? XeOF2. All right. All right. I'm assuming that xenon goes in the center because it's the biggest. Well, let's see, that's 8. That's a 6, and that's 2 times 7 is 14. So that's 28. Right? Yeah, 28. So we put that one there, put an oxygen here, put a fluorine there, and put a fluorine there. 2, 4, 6. 22 electrons. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17, 18. Okay, so this has 1, 2, 3, 4. Let's see. Xenon exceeds the octet, and the rest of them are happy. So 1, 2, 3, 4, 5. So the electronic structure is 5, which is a trigonal bipyramid. Okay. So what happens to a trigonal bipyramid when you do one of these numbers? I put xenon in the middle. Like that. Where do the lone pairs go? The lone pairs tend to go on the triangle part. Right. So if we turn it around, because this one's going to be, I would put the oxygen here and the fluorines out here. So if you turn it around like this, put the oxygen out here, and the fluorines down there, then you get a T shape. Okay. All right. Number 44. Select the correct molecular structure of silicon tetrahydride. Okay. So, Lewis dot structure. Silicon is with carbon, so it's got 4, that's got 4, so we have 8 electrons. Silicon, hydrogen, 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 hydrogen. 2, 4, 6, 8. That's it. So 4 groups means tetrahedral. Which would be B. All right. That one went quick. 44. Let's scroll down. 46. Let's see. I can't do that, so let's do like this. There we go. 46. Select the correct molecular structure of beryllium dichloride. Beryllium dichloride. Okay. Beryllium. It's an alkaline earth, so it's got 2 electrons, 2 valence electrons. Chlorine has 7 each, so that's 14. That's 16 total electrons. Beryllium, chlorine, chlorine, 2, 4. That leaves us with 12. 2, 4, 6, 8, 10, 12. All right, so what are we going to do? Excuse me, beryllium, not boron, beryllium. Well, 2, 4, 6, 8, 10, 12, 14, 16. That's right. Okay. So beryllium needs an octet. So let's take these 2 here and these 2 here. And it's still got 2 groups around beryllium, so this is a linear molecule. Right? 2 groups means linear. That's 8. 6. And let's see. 48. In the molecule xenon difluoride, how many pairs of electrons? Got to move something out of the way here. How many pairs of electrons surround xenon, and what is the molecular geometry? Okay, so we're starting from this one. We want to know how many pairs of electrons surround xenon. Doesn't say what kind of pairs, it just says pairs. So we got xenon is 8 because it's a noble gas. 2 times 7 is 14, so we have 22 electrons. Xenon Got a fluorine there and a fluorine there, 2, 4. 18. 2, 4, 6, 8, 10, 12. Okay, so that means 6, right? Okay, 2, 4, 6. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, everybody's accounted for. How many pairs of electrons surround xenon? Okay. That is a misleading question, because these can be counted as a pair also, one bond. It should say how many lone pairs of electrons. Lone pairs, so you have 3 lone pair. And you have 1, 2, 3, 4, 5. You have 5 groups, which means trigonal bipyramid. Trigonal bipyramid electronic structure. But if we draw it, remember, when a trigonal bipyramid with xenon in the middle, where do the lone pairs go? The lone pairs are going to go on the triangle. So you have a fluorine here and a fluorine here. That is a linear molecule. Right? So C is the answer. This is linear. This is the electronic geometry. This is the molecular geometry. All right, that's 48. 49. Okay, we can still see everything. Let me scooch it a little bit. I don't want to do that. 49. 49. Choose the member of each set that best matches the label. Oh, okay. More metallic. Beryllium versus what? Barium. Let me put them all up here first. This is metallic. And the next one is covalent. And we've got N2O gas versus MgO solid. And the last one, highest electronegativity. So more metallic, more covalent, highest electronegativity. O, S, and Br, right? Okay. The first one, metallic. The more metallic one is lower left-hand corner of the periodic table, or to the left if it's in the same period. So barium and beryllium. Actually, barium and beryllium are in the same group, right? They're in the same group. So barium is further down, which means it has lower electronegativity. That means it's going to give up its electrons more easily if it's confronted with a nonmetal. Right? So barium is the more metallic. All right. So if we look at our choices, B, C, or E. So from this choice, we have B, C, or E are possibilities. How about this one? Which is more covalent? The more covalent in this case is the one with 2 nonmetals. If you got a metal and a nonmetal, it's less covalent. In fact, it's ionic. So this one is the second one. So out of B, C, or E, which one is N2O in? It's in C or E. So this one says it's either C or it's E. Now we have to say which one of these is more electronegative, right? lower left to upper right makes more electronegative. So we look at our periodic table and we find that, say, oxygen relative to positions here, sulfur's down here, and bromine is way down here. So oxygen would be the more electronegative. And that would be E. Okay, that's 49. Let's see, 49 and then 50. Okay, let me move my image out of the way here. There we go. I think I need a new marker. Here we go. Number 50. All right. Use the bond energies given below to calculate the enthalpy change for the reaction. Okay, let's write the reaction first. HCN gas plus 2 hydrogens gas yields CH3 NH2. Let's see, that's hydrogen cyanide, that's hydrogen gas. This is methylamine. Okay, what we need to do is remember that to calculate the enthalpy for this reaction, the enthalpy is equal to, be sure I get this right. Right. So what we want to know is the sum of the energies for the bonds, energies for bonds broken. That would be this side, the bonds broken on this side, minus the sum of the energy of the bonds formed. Right? When you look at it this way, then it's easier to determine that these bonds have to be broken, which means reactants come first. Then we minus the energies for the bonds that are formed, because the energies for all of these bonds, the energies for all these bonds are always positive values. Bond energies, like I said earlier in the class, bond energies mean how much energy do you have to put in to break the bond? So it's always positive, right? You're adding energy to the system, so it's a positive value. Okay. So what we need to do is assess what are the bonds. Remember, hydrogen cyanide is like this. Okay. Hydrogen is like this. This methylamine is like this. Okay, so those are your bonds. So we've got on this side, we have hydrogen and carbon, which is what? Hydrogen carbon is 413 kilojoules. And there's only one of them. So it's 1 mole, kilojoules. Then a carbon and nitrogen triple bond is 891 kilojoules. There's only one of these. Then we've got a hydrogen-hydrogen bond, which is 432, but there are 2 of them. Okay. So if we add those up and find out how much energy it takes to break the bond, then we're going to get 413 and 891 plus, and then 432 times 2, add that together. So this is 1755 kilojoules on this part of the equation right here. The other side is 1, 2, 3. Let me label these. This is hydrogen carbon. This is carbon triple nitrogen. And this one is hydrogen hydrogen. Okay. On this side, we've got carbon hydrogen. So what's carbon hydrogen? 413 times 1, 2, 3. Then we've got carbon nitrogen, which is 305. And there's only one of them, right? Because there's one here. So there's only 3 of these, there's only one of those. And now there are 2 of these, nitrogen, hydrogen. So 2 times 391. There we go. So what's the total here? 413 times 3, and then 305 added together, and then 391 times 2, add that in there. So I get 2326 kilojoules. So now all we need to do is subtract this one from that one. Right, minus 2326. And that would be a minus, right? We know this one's bigger than that one. So this is minus 571 kilojoules. Now, why is it 158? What did I do wrong? 2. Hold on a second. Let me see what I did wrong. I added those wrong. Let me do that again. 413, 891, and 432. Okay, 413, 891, and 432 enter 2 times plus. Yeah, that's my mistake right there. 2168 minus 2326 minus 158. There we go. So that's B. All right, that was 50. All right. 51. Given the following information, calculate the change in enthalpy for lithium plus hydrogen bromide yields hydrogen gas plus lithium bromide solid. Okay, this is going to be calculate the enthalpy. All right, so this is going to be like a Hess's exercise, adding the equations in the right order and with any multiples. What effect does it have on the individual heat values, and then you can add them together and find the enthalpy. Okay, so our target equation is 2 lithiums solids. In this case, the phase matters. Because there's some of these that are just pure phase change, and we need to keep track of that also. Plus 2 HBr gas yields H2 gas plus 2 lithium bromide solid. All right. So where do we start? Well, let's see. We can start from the top. We're going to need solid on this side, right? So that works. If we do lithium solid yield, I'm going to try to keep these arrows lined up. And then lithium gas, right? That puts lithium on the correct side, but we need 2 times that. So the value for the enthalpy for that particular process is 166 kilojoules per mole. So 166 times 2 gives us this one. And that takes care of these 2, those 2. All right, let's do it this way. 2 here and 2 here, so we don't lose track. We don't lose track of our coefficients. All right. Now, how about HBr? We need HBr gas on this side. Okay, there it is. HBr gas, and we need 2 of them. Okay. Yields H gas plus Br gas. This is the heat, the bond energy for HBr. And we need 2 times whatever that value is. Right? So this is going to be 2, and this would be 2, and this would be 2. 363 times 2. Okay. So that takes care of this one. Hydrogen gas needs to be on the right-hand side. The last one is hydrogen gas, but it's on the wrong side. So we need to flip it. Right? We need to have 2 hydrogen atoms yield 1 hydrogen gas. So there's our hydrogen gas, there's this. So all we have to do for this one is change the summary. 432 is a negative. Okay, that takes care of this one. How about lithium bromide? That's probably going to be lattice energy. Lithium bromide on that side? Yes, there it is. Lithium bromide solid. And that is formed from lithium gas there, plus bromide ion gas. Is that it? Lithium, bromine? Yes. And how many do we need? We need 2 of them. So 2 here, 2 here, 2 here, and 2 times the value. Minus 809. Okay, and these are all kilojoules. Okay, so we got this one. All right, now let's check off the ones that we have. This one, this one, this one, and this one. That means that we've added some things that have to be canceled out. Let's see if we can cancel any of them at this point. Here's 2 hydrogens. Those go out. Okay. Let's see, there's a lithium ion. No, can't cancel that one yet. Bromide? No, that's bromine. Atoms. This is bromine ion, so we can't cancel those. All right, so what we need to do is find a way to cancel this lithium gas. So where's lithium gas? Lithium gas, there it is. The third one down, ionization energy. So lithium gas yields lithium plus gas plus an electron. Right? But we need two of them. So we need 2 times the value. We didn't change its order, so it's 520 times 2. There we go. So that gets rid of this one that we never needed, right? And this one gets rid of that one that we didn't need. All right, what do we got left? Check, check, crossed out, crossed out, crossed out. We need bromine. There it is, electron affinity. Only bromine's on the wrong side. We need to flip it back to this side. So we need bromine, gas, yields, bromine atom plus an electron. But we need 2 of them, right? So we need 2 here, 2 here, 2 here. Is that right? Just a second. We're not going to be able to cancel electrons. Right, electrons on this side. This one, we needed this way to cancel those lithiums. Cancel these lithium ions. Yeah, ionization energy. Okay. So how do we get rid of those electrons? We may not have to. We're trying to get rid of, oh, whoa, 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 whoa. No, I got it backwards. We need to get rid of this one by doing this. There we go. Right, electron affinity for bromine. We'll cancel this one. And the electrons will cancel. So we need 2. And are we doing it in the right order? Bromine plus electrons? Yes. So minus 325. There we go. Now the bromines cancel and the electrons cancel. And the bromine ions cancel. So that's it. We got everything checked off and we canceled everything that wasn't supposed to be there. So now all we have to do is multiply and add all those together. So 166 times 2, 363 times 2, and add those together, then 432 subtract, and 809 enter times 2, subtract that, and then 520 enter times 2, add that, and 325 enter 2 times and subtract that. So I get minus, rounded off, minus 602 kilojoules. There it is, B. That took a lot of work. Okay. The next one's going to take some work too. $52. All right. Calculate the lattice energy for rubidium chloride from the following data. All right. In this case, it's got abbreviations in there, and we need to know what those abbreviations mean. So let's sort out what those abbreviations mean. Rubidium solid to rubidium gas. That's sublimation. Rubidium solid to rubidium gas, sublimation, and the heat for that is 85.8 kilojoules. Okay. The next one, IE1, that's ionization energy, first ionization energy for rubidium. So how do we write that one? We have rubidium gas, which yields rubidium 1+ gas plus an electron. I need to move this over, don't I? 85.8. Okay. So what's the energy for this one? 397.5. kilojoules. What's the next one? BE for Cl2. BE for Cl2. That's bond energy. Bond energy for Cl2. That's a gas. And it's going to 2 Cl atoms. That represents the equation for bond energy, which is 226 kilojoules. Okay. Then delta HF for rubidium chloride. So this is the heat of formation. How do we write that? Remember, the heat of formation for rubidium chloride, this is a gas. No, this is the most common, this is the most stable form at 1 atmosphere pressure and room temperature. So this is a solid. And it's formed from the elements. So rubidium would be a solid, and chlorine would be a gas. But we only need one of them. So it's like that. 1 rubidium plus a half of chlorine yields rubidium chloride solid. And that value is minus 431. Okay. And the last one. The EA for chlorine. Electron affinity. Electron affinity for chlorine. So that is chlorine gas, like that, plus an electron yields chlorine minus gas. Okay, so that'd be minus 332. Okay, I went to all that trouble because you have to understand what those abbreviations stand for and what they mean. Otherwise, you can't add them together to find the answer to lattice energy. So the lattice energy for rubidium chloride rubidium is an alkali metal, so it's 1+ charge. Chloride is a halogen, so it's a -1 charge. And we're forming this rubidium chloride solid from the rubidium plus gas and the chloride minus gas. That's our target equation. We've got to rearrange these and put them in there so that we can add them together with Hess's law. And then we can add the enthalpies together. Okay, so rubidium plus, where's rubidium plus? Here it is. So this one needs to be flipped. So if we put this one up here, rubidium plus as a gas, plus an electron yields rubidium atoms as a gas, and that's reversed. So we have to change the sign, -397.5 kilojoules. Okay. So we got this one and this one. Now, how about chloride? Here's chloride. Here. So chloride needs to be on this side also. Chloride minus gas. And the other side is chlorine atoms plus electrons. So we have to change the sign on this value. So this is a +332 kilojoules. All right, takes care of this one and that one. Okay, now rubidium chloride solid. Here's rubidium chloride solid right here. It needs to be on that side just like it is. And we'll just transpose this one over here. So rubidium solid plus 1/2 chlorine gas yields rubidium chloride solid, and that's -431 kilojoules. Okay, takes care of that. And we've used this one. We've used this one. And we've used this one. So what can we do with the rest of it? Because that. Now we've got rubidium gas here. How do we get rid of rubidium gas? We need the rubidium gas on this side. Right. So we put this one over here. Gas, rubidium, solid. So we've inverted the equation. This one needs to be a negative, 85.8. All right. So now we've used this one. And we've taken out that one and that one. And this one. There we go. Okay, what's left? Chlorine, diatomic chlorine yields monatomic chlorine. And we've got this chlorine right here. So this chlorine needs to be on the other side. So we have 2 chlorine gas yields Cl2 gas. But we only need half. Right? So we'll take a half of that. And we'll take a half of this value, which had to be reversed. 226 divided by 2. Okay. So now we've used this one. All right, so let's change this so we don't get messed up with our coefficients. That's a single, this is a half. There we go. Okay, so we've gotten rid of this one here. And this one right here. Okay. And we've used them all up. Now, did we do everything we needed to? That was there, this one's here. And this one's here. And this electron also cancels. There we go. So now we've got these values canceled, 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 and canceled. So we don't have anything outstanding. All right, so we need 2 divided into 226, which is 113. That's a negative. That's a negative 113. Okay, so we're going to add this one, this one, this one, this one, this one. There we go. So 397.5, change the sign. 332, add together, 431 minus, 85.8 minus, and 113 minus. So I get the lattice energy of rubidium chloride, if I did it right, is minus 695 kilojoules. There it is. All right. And next, okay, 53. Let's make some room. Okay, 53. All right. In spite of large electronegativity differences between bonded atoms, beryllium chloride has no dipole, while sulfur dichloride does have a dipole. So beryllium chloride is one, and then sulfur dichloride is another. Okay, and we're told that beryllium chloride has no dipole. No dipole. While this one does have a dipole. We need to explain it. All right, so we need to write the Lewis dot structures for each one. Beryllium has 2 electrons, and 2 times 7 is 14. So we have 16 electrons. All right, beryllium with a chlorine and a chlorine. So that's -4 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I think we did this one before. We can give beryllium an octet by moving these over here, moving those over here. So we got a double bond here and double bond here. And these 2 are gone. Okay. Now, what's the structure here? Well, we're going to have the bond polarity is this way. But it's equal and opposite, right? 2 groups means linear geometry. And since there are no lone pairs, the electronic geometry and the molecular geometry are the same. So this is a linear molecule with polar bonds, but they're opposite and equal, so they cancel. That's why we have no dipole for that. Okay. How about this one? Sulfur. It has 6 electrons, and 2 times 7 is 14. So we have 20 electrons. Right. Sulfur, chlorine, chlorine, 2, 4. 16. We have 2, 4, 6, 8, 10, 12. We have 4 electrons left here, 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 here. Now we got an octet here, we got an octet here, we got an octet there. All right, so what's the electronic geometry of this molecule? It's got 4 groups, so it's a tetrahedron. Okay, so if we do that tetrahedron thing, here, 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 and sulfur's in the middle, and then we have something up here. Right? Let's put chlorine here, we put a lone pair there, and then we've got a lone pair up here, right? Form the tetrahedron. Okay, that's the electronic geometry. But the molecular geometry is bent. And we've got dipoles this way and this way, which means we would expect the overall dipole to be that direction. That's why this molecule is polar. It has a dipole moment because it has polar bonds, and it has the bonds, the polarities do not cancel one another. Okay, for an overall dipole. All right, let's see what's left. There we go. For ICl4 minus, this is 54. ICl4 minus. All right, we're asked to draw the Lewis structure. Okay, so we have 5 times 7 is 35 plus 1 is 36. 36 electrons. Okay, so we have I in the middle. We have 4 chlorines. Right, 2, 4, 6, 8. So that's 28 electrons left. 2, 4, 6. 2, 4, 6, 2, 4, 6, 2, 4, 6. So 4 times 6 is 24. And that's 4 electrons left over. So we have to put 2 there and 2 here. That's 1, 2, 3, 4, 5, 6. 6 groups means an electronic geometry of octahedron. Okay, so when we do that, when we draw the octahedron, right, we've got a square here, we've got I down in the middle, and we've got something up here and something down here, right? So what goes out here and what goes up there? Well, for octahedrons, the lone pairs tend to go on the apexes, and we got 2 of them. And the rest as chlorine. Okay. Now, this is not complete yet. If we draw it that way, got to have the charge. Without the charge, the total electrons in here are not accurate. Right. So we have that, and that. There we go. So that would be the Lewis dot structure. The shape of the molecule, well, it's octahedral electronic, but cover up the lone pairs and you get a square planar. Square planar molecular geometry. Okay. And is the molecule polar or non-polar? Well, the bonds right here, the bonds would be slightly polar because chlorine is more electronegative than iodine. But they're equal and opposite in all directions. So they cancel one another out And this is a non-polar molecule. Okay? There she goes. And that's it. We are done for this review. Now, let me check my what to say changes. I didn't make any changes. Okay. That's okay. Let me check to be sure what's on the agenda. I think we just have an exam next Thursday. Be sure. Yes. So the only thing we have on the agenda for 2 days from today, Thursday, is the exam on this material. That's it. If you come in person, take the exam, I'll grade it immediately and you can leave. Or you can take it on Brightspace. Now, Brightspace may require that you, the exam may require that you draw some things based on what we just did here. So it may be difficult for you to complete the exam all the way in Acrobat. You may have to fill in all your multiple choice answers and then print it out. And then fill in the handwritten part, or you could do it on a separate sheet of paper. And then either submit them separate documents for the exam, or if you draw on the exam, then you can take a picture of it and submit that. Okay, that's it. We're done.